Hello, Dr. Jaran, can you hear me?
Hello, good morning. Yes, I can hear you.
Okay, let's wait a few more minutes. We have a good RSVPs that people are stabilizing. One minute, and then I can make the intro. So while people are joining, let's have some networking session. And if you don't mind to share where you guys joining from, maybe you're welcome to share your LinkedIn as well. We always recommend networking. That was the original purpose of the meetup groups before COVID started. It was in person. And then, network is everything, actually. You can share with everyone, not only hosts and panels. So you can get a good network of data scientists in your network. So, yeah, I see people joining from everywhere. London, India, South Dakota, and Los Angeles, San Francisco. I actually share my LinkedIn as well. San Jose, Toronto, North America, New York City, Philadelphia. That's good. This is like a post-COVID effect in our meetup groups that is a huge network. And that's great for networking too. You will have people in your network. They are either data scientists or potential data scientists. You'll be connected with. And there's Santa Clara. I mean, we are based in Santa Clara. I will expect actually more than help from Bay Area, but it's interesting all over the world. A lot in London. So, yep, we have Justin Fremont across. We haven't seen another London. Yeah, some people only share with the host and panels. It's just your preference. It's fine. Good. Then our numbers increase since we've started. Yeah, you're welcome to share your LinkedIn or where you're joining from. It's a great networking, and you see that people all around the world, they're ambitious for the AI and data science. So I will make a short intro. My name is Murat. I changed my name here so people can see. I'm Stanford scientist in School of Medicine, been 10 years here, and background on physics, biophysics, bioengineering, have been doing AI all my life. And I'm co-founder of Magnimind Academy with Dr. Jaran. And then we had a couple of other Stanford colleagues. We started that years back with meetup groups. Now over 30,000 members we have. Our goal is to address the gaps in AI data science training. That was our initial focus, and it's been going on that for past 8 years. And yeah, I think we believe that we are leading in this training of AI. So what we have meetup groups, if you're not part of any meetup groups, welcome to join those meetup groups. But I believe most people come from this meetup groups. We have 3 in the Bay Area. We have in Los Angeles, Chicago, New York, London. And we have additional cybersecurity because people demanded cybersecurity. We have that meetup group as well. We have websites. We have other social media channels. I'm actually gonna copy paste YouTube again. We have YouTube channel. There's our courses are shown in YouTube. Our recorded sessions are there. You may not be aware, but our YouTube channel is so rich. If you are in data science field or going to join the data science field, we have so much content from different domains. There are workshops, there are career events, there are other things in YouTube. It is very enriching. And you can ask your questions from Q&A sessions. And we're not letting people to talk because so many here, everyone wants to talk. We cannot finish it. You're welcome to ask your Q&A sessions, any questions, Q&A. Is that right, Dr. John? You prefer Q&A? They have questions? Okay.
Yes. Yes, because we're posting a lot of messages, and then sometimes questions can be lost.
So what I will do now, we have actually a deadline for in 2 days. We extended our deadline for a new program in 2 days. We have a special bootcamp for data scientists, for data science. I'm going to share briefly and talk about a few minutes. We have a data science mentorship slash internship program. And this program is in, okay, yeah. So it is deadline in Monday. So we do last emails. If you maybe don't know it, you can just learn about it. You can send us email more information too. So there are three problems for people to find the jobs in the field. One is they don't really work on real world projects. There are a lot of lack of experience, and they have a limited mentorship. The students come to us, sometimes they have masters, they have bachelors in data science, and they actually did boot camps too. But when they come to us to the projects, because we have project-based training, we see that they are really lacking a lot of skills, but they cannot even build a full pipeline themselves, because when companies want to hire, they don't want to work extra months or wait for your extra months to do any full pipeline project, and they don't have many times another data scientist. So there is a big gap, and they really look for someone who's ready to do projects and have an experience. So what we give in our bootcamp, we give real world projects. We give 5+ mentors, as literally we give 5+ mentors in our projects. So each one is specialized in different areas of data science, and you'll be connected throughout the bootcamp with that 5 mentors. And we provide company experience because part of the program, it is with a company that we're affiliated with. It's an internship, and you can show that experience in your CV. And our academic crew is from Silicon Valley companies and academic, like people like Stanford University, San Jose, Santa Clara, Berkeley. And we give a strong Silicon Valley exposure. So just a summary, we have projects, we have mentors from top companies, we give practice interviews, we have full online class open like 8 hours, and along with the mentors, we have career coaching, we have interview Q&A sessions, and resume support. Not only we prepare them to the projects or to get the job interviews, we also prepare for interview process with our interview coaches. So that's a simple summary. We just share the link. You guys can learn more about it and have any questions. So today, Dr. Jeran is our co-founder, is in faculty in Magnimind. He's also faculty in San Jose State University. Similar to mine, he's been working on computational field last 20 years in Case University and Santa Clara University. He was faculty prior to current position. And we've been doing those work for last 8 years. I won't take it much longer and let Dr. Jeran lead.
Thank you, Dr. Badaei. There's one question. What is the charge for the boot camp? And then it says last day is 3rd September. I didn't get what it is, but I think
so we extended to Monday. Yeah. The price for it goes $6,000 to $10,000, $6,000 upfront, and $8,000 in monthly installment, $10,000 income share, but there's a limited option in there. For actually what we do now, we have a promotion. If someone is not qualified yet, because we look for intermediate to advanced level people who have studied but not there yet, we give 2 months additional period with the additional mentors. That 2 months comes in free. Usually we charge $2,500. So total program with upfront payment will be $6,000, even though you need additional support. It will go from 15 weeks plus 2 months.
Thank you.
Dr. Jeran, you may start.
Thank you. Thank you very much. So hello, everyone. Good morning, good afternoon, good evening. So let me share my screen. And also, I'm going to send you the link to the materials. Just 1 second, if I can find the from chat. Okay, so I'm sending you the link to the material for today. All right, so you can download it. Here it is. Okay, so in this folder, the link takes you to the folder. You will find these files. Okay, so that's what we're going to follow today. All right. So as you are downloading the file, let me go over the plan for today. So this is a very important topic. You may be in the marketing department launching a new marketing campaign, or you are launching a new product, or thinking about making a change in your product. You need to run A/B tests, right? So you need to see how people are going to, users are going to react, right, to the changes you are making. So that's the goal of this 2-week workshop. So we are going to work on, try our best to understand how we can run and then evaluate A/B tests. Okay. So before we start with A/B tests, my goal is let's first go over statistical hypothesis testing so that we understand what hypothesis testing means. And then maybe a little bit about SciPy, and then how we can actually create random variables, what is probability density function, how we can measure PDF given some distribution or cumulative distribution function, right? So how we can generate random variables, how we can simulate what is that, a test. And then, so let's do some practice together again this week. And then next week, the main topic will be A/B test itself. Right. So again, at first, I'm going to very quickly go over review of hypothesis testing, and then there's a lot of coding. This time I gave the code, but what we are gonna do is, and I strongly recommend, please type the code one more time yourself, and then look into details. So what is happening at each line, and that's what I will try to do. All right. So first of all, hypothesis testing. Whenever you, my assumption is we heard a little bit about hypothesis testing, but we may not know the details. That's my assumption about participants today, okay? So we heard about hypothesis testing, right? So what is hypothesis testing? In general, what we do is there are two hypotheses. One is, we call this hypothesis 0 or null hypothesis. We call it, if you don't know Python, what you can do is you can open this session. We can open this file. Let me move this thing aside, okay, to the other screen. So if you don't have any IDE already installed and then you didn't do any Python coding, my recommendation is please learn statistics with R or Python. So in this case, we are going to use Python. Again, for you to run the code, what you can do is you can search for Google Colab. Yeah, Google Colab. So Google Colab is going to bring you, because I already had a lot of files from previous. So when you first open Google Colab, this is what you're gonna see. Okay, this is what you're gonna see. And then on the left panel, so there is this folder icon. Okay, this says files. When you click on this, okay, wait for a while. And then if you like, you can upload a data file to this session. That's one thing we're gonna do. But before doing this, what you can do is you can click on file in here, file, and then you can say open notebook, okay? Open notebook, or you can upload a notebook. So let's upload a notebook because I already shared the notebook with you. So when you click on upload a notebook, so you're gonna browse the notebook in your folders and find the notebook and then just open it here. So you can run the code with me using Google Colab if you never used Python before, okay? All right, so let's get back to the discussion. So in general, we have two hypotheses. We're gonna call one of them H0. We're gonna use letter H and 0. So this is called null hypothesis. Okay. And then we have a second hypothesis. We're gonna call it H1. And this is, we're gonna call it alternative hypothesis. Okay. So there are a couple of misconceptions or things that maybe we remember incorrectly about null hypothesis. So what we do is with null hypothesis, for example, we are going to make a change in our website. Okay, what kind of a change? So we are changing the color of a button from from say yellow to red, right? So that's a very simple change. We are changing a button on the side from yellow to red, and then we wonder, how people are going to react this. Maybe that button is about clicking on a link, maybe an advertisement link or sale link, right? So we just wonder what is the impact of clicking on that button on, what is the impact of changing the color on people's behavior, right? So what we're gonna do is our null hypothesis, H0, is going to assume that this change has no effect. The change has no effect, okay? So this is going to be our null hypothesis, right? And our alternative hypothesis is the change will have an effect. Okay, so these are our two hypotheses about this this change, right? So that's one example on when I say we're gonna test hypothesis. That's one example, right? The change has no effect versus the change will have an effect. So another example. Let's first understand what hypothesis means. Another example. Again, this is a very general example we are using. So let's say we are manufacturing, producing chocolate, right? And then each box of chocolate, right, is supposed to weigh, right? Let's say it's a big chocolate package, 1 pound, okay? All right, so that is what it's supposed to be, okay? So then our null hypothesis is each chocolate box is 1 pound, okay? Right? And then our alternative hypothesis is each chocolate. Look, it's very simple. We're not gonna say it's 1.2 pounds. It's very difficult, right? We can say that, but that's not what we're gonna do. Each chocolate, by the way, very bad pronouncing chocolate. Okay, chocolate, and then you understand, right? So chocolate, you understand this. Okay, is not 1 pound. Okay, so when I say not, it doesn't weigh 1 pound. Okay? This is another way of creating two hypotheses. One is null hypothesis, the other one is our alternative hypothesis. Okay, so what is our goal? So what are we trying to establish here? Are we going to say, hey, we ran a test, and then I tested my hypothesis, and I say null hypothesis is correct. So am I gonna say, am I going to claim this at the end of hypothesis testing? So again, I'm repeating my question. Am I going to claim that H0 is true? Is that what I'm trying to do? Okay, so the answer is no. Okay, the answer is no. I'm not going to claim that H0 is true. What I'm gonna do is, given some data, I have some data. So here, what is the data? I'm trying to see if the button, change the color of the button has an effect. What is the data here? I'm going to see how many people clicked on the button when it is red, how many people clicked on the button when it is, or what ratio clicked on the button when it is red, what ratio clicked on the button when it is yellow, right? So this is the data I have. What is the data I have? I'm going to sample chocolate boxes from the factory. I cannot weigh all the chocolate boxes. Out of, say, 10,000 boxes, I'm going to maybe sample 200 of them. I'm going to weigh them and then see what is the weight of each box, right? And then I'm going to use this data to use data. I'm going to write what I'm saying, use data to check if I can reject H0. This is what I'm trying to do. Okay, please try to make a distinction between this one. I'm not going to claim that H0 is true. I don't have enough variable, enough data, enough input to actually make that claim, okay? But I might have enough data to check if I can reject H0. And then when I say if I can reject H0 with some confidence, okay? So again, I'm not going to say 100% I'm rejecting. I'm going to say I'm rejecting. I have enough confidence or this much confidence to reject H0. Okay, this is what happens if I reject H0. If I reject H0, I'm going to fall back to the alternative hypothesis. I'm not saying alternative hypothesis is true. I'm not saying that. All I'm saying is I have enough evidence, okay, or confidence to reject H0. That's all I'm doing. Okay. Then what if I don't have enough confidence to reject H0? Here is the wording I'm gonna be using. Okay. I will fail to reject H0. Look, this is, I'm using Python, okay? This is not equal to H0 is correct. Please make this distinction, okay? So I will fail to reject H0 because I don't have enough evidence. Data is not giving me enough evidence to reject H0. This doesn't mean that H0 is correct. It only means that I don't have enough confidence. So to actually reject that each chocolate box is 1 pound. I cannot say it is not 1 pound, that's all. But I'm not saying that it is 1 pound, okay? All right, so this is a very important distinction. So this is what we're gonna do. We are going to use data and we're gonna use our statistical knowledge to be able to say whether we can reject the null hypothesis or whether we can fail to reject null hypothesis, okay? And again, this doesn't mean that any of the hypotheses, we are not making the claim that any of the hypothesis is actually correct, all right? Okay, all right, then let's go over this hypothesis testing. Again, without code, as of now, there is no code. We're gonna start coding step by step, okay? Try to understand what's happening. Okay, so first of all, let's go back to this chocolate box example. I think all of us, I'm assuming, okay, this is another assumption, we can test it, all of us like chocolate, right? So let's look at this example, again, H0. Box is, I'm going to be more formal now, Mean is 1 pound, okay? What is mean? The mean, if I had a chance to weigh all the chocolate boxes, and then if I took the average of that, let's say there are thousands of chocolate boxes, I took the average of them, then the average is 1 pound, okay? So that is what my null hypothesis, again, the link to the material is here. Okay, then what is my alternative hypothesis? Alternative hypothesis is mean is not 1 pound. Okay? That is my alternative hypothesis. Again, what does this mean? The mean of the chocolate boxes, the weight of the chocolate boxes. Okay, so this is at the beginning my assumptions. The first assumption is mean is this, the second mean is not this. So what do I have? What do I have to test these hypotheses? So maybe I will measure the weight, let's say record the weight of 100 boxes. Okay, I will record the weight of 100 boxes. Okay, that's all I have as of now. It's not practical for me to go over all the boxes one by one. I'm just going to randomly sample 100 boxes. All right. Okay, now these upcoming figures are important to actually internalize what hypothesis testing means. Again, we are going to write the code in a minute. This is what I'm testing. This is what I'm testing. This is what I have as data. That's all right? So here is how I'm going to start testing, okay? First of all, I'm going to start with the assumption that my null hypothesis is correct, okay? That's my assumption. Again, I'm not gonna make this claim at the end. That's my assumption. Now it's a big if the mean of the chocolate boxes, if I were to measure the weight of all the chocolate boxes, which is impractical, if that was the mean, okay, if that was the chocolate box population, okay, and then that mean is 1 pound, if that is the case, then if I keep sampling from these chocolate boxes, let's say I'm gonna take 100 box, measure the weight, put it back. Take another 100 box, measure the weight, put it back. Another one. Let's say I'm doing this repeatedly. Again, this is impractical. I will not do this. But let's say I'm doing this, okay? From the chocolate boxes population, my assumption is the whole population has an average of 1 pound. But of course, individual boxes are going to be different. Some of them will be 1.2, 1.1, 0.9, but on average, 1 pound. What I'm doing is I'm taking samples from this population. Okay, 100 boxes, put it back, 100 boxes, put it back. okay? If the average is 1 pound, if I keep sampling from this population of chocolate boxes, and if I were to draw the average weight of those samples, okay? So again, I'm taking 100 samples of 100, taking the average of that, okay? And then I repeated this many times, many thousand times, okay? Again, impractical, an assumption. Then the distribution, when I say distribution, what I'm saying here is, let's say out of 1,000 samples, and each sample has 100 boxes. Let me write it here. I picked 100 boxes 1,000 times. Let's make it 10,000 times, okay? Let's say, okay? All right. And then I measure the average weight for each 100 boxes, okay? Let's say, okay, average. And then I plot the histogram, or let me call frequency of average weights of these samples. When I say sample, I'm referring to 100 boxes. Remember, I have 10,000 samples. Each sample has 100 boxes, and I measure their weight. So it's something like this: M1, M2, M3, all the way to M100. I'm sorry, 10,000. Each M is the average weight of 100 boxes. Okay, so these are some numbers. What I'm doing is I am putting these numbers into a histogram. I'm creating a histogram of these numbers. In other words, I'm putting these numbers into bins. So let me make it more specific. How many of these numbers fall into the range of, because these are average numbers, into the range of 0.8 and 0.9, okay? Okay, and then how many of these numbers, when I say numbers, remember, these numbers are the average weight of 100 boxes, fall into the range of 0.9 and 1, and so on and so forth, 1 and 1.1. So what I'm doing is I'm creating bins, and I'm putting these numbers into these bins. Then this is called histogram, right? Then I see how these frequencies are actually appearing, right, on a distribution curve. All right, so let's say this is what I say. Let me make this a bit smaller. Again, this is my null hypothesis. This is the mean that I assumed it was correct from my, again, what was it? 1 pound. So if the real mean of the average mean of all the chocolate boxes was 1, and if I had repeatedly took 100 samples from these boxes, the average weight of these 100 box samples out of these 10,000 samples would be centered around this mu number, right? We have a theorem for that. Let's not get into it. We have a theorem for that. Let's not get into it. Okay. And then some of the averages are 0.9, some of them are 1.1, and then very few of them will be like 1.4, 1.5, right? We're going to have really a few number of boxes which are much bigger than 1, and we're going to have a few a few boxes which are much smaller than 1 pound, right? So, but majority of the boxes will be weighing 1 pound. So this is what I would see if this was the case. Okay, I hope you guys are with me up to this point. Again, we're gonna write the code soon. Okay, now, next. So I established if my null hypothesis was true, this is what I would observe. So, and then when I look at this distribution, remember, this is the mean, the average of the population. So these cases which are falling too right to the, very right? So towards the end of the tail of the distribution, or towards the left end of the tail of the distribution. So average number of weights of the boxes which are much lower than mu and which are much bigger than mu are rare, right? It's not that it's a very, very rare thing to see. I wouldn't see too many boxes if the average is 1 pound. I wouldn't see too many boxes with maybe 0 boxes with 0.2 pounds, or maybe 0 boxes with 3 pounds, right? They're going to be 0. There is no such box. Okay. So please understand that these are the portions of this distribution. Again, assumption is my null hypothesis is correct. These are the left and right tails of this distribution is the place where representing very rare occasions of events. Okay. All right. Now, what I'm gonna do is, remember I only recorded the weight of 100 boxes. That's all I could do. That's all I could do. I cannot actually, measure 100 boxes repeatedly. That was just an assumption. That was just a, let's say, right? But this is the real case. I'm able to record the weight of only 100 boxes. That's the practical. So I will take this 100 box weight, the average weight. Let's say it is 1.1. Let's make it a rare case. It is 1.5. Okay, the average of these boxes is 1.5. Now I'm gonna come here. Remember, this is 1. This is 1. This is the average from my null hypothesis. And then average of the 100 boxes that I measured is 1.5, which is falling here. So what does that mean? This 100 boxes, their average, is a very, very rare event if the true mean of the chocolate boxes was 1 pound. Okay, if my null hypothesis was correct, then the average of these 100 boxes that I actually recorded, the average weight of these 100 boxes, appearing in this shaded area, which is indicating the rare occasions given at the assumption for the null hypothesis, right? That means these 100 boxes, having these 100 boxes with that much weight is something extremely rare. Okay, so there are 2 reasons for this happening. When I say this, there might be 2 reasons why I have 100 boxes, which average weight of these 100 boxes is actually too different than 1 pound, which was my assumption at the beginning. There might be 2 reasons. Why? One, yeah, by chance, right? Sometimes we might have some boxes which are bigger than 1 pound, and by chance, I randomly pick those boxes, those 100 boxes, which again, by chance, are greater than 1 pound. So, but that chance is extremely small. That chance is extremely small, right, for it to happen. That's the first explanation. Now, we are just reasoning, okay? This is the first. The second explanation is, hey, this distribution is based on the assumption that average of the weight of the chocolate boxes is 1 pound. And then I saw that the 100 boxes that I measured is far away from 1 pound. Then it makes me think that, hey, maybe the true mean of the population is not 1 pound. Maybe this distribution was towards right. It was something like this. Let me try to measure. I'm sorry, let me try to draw it here. Okay. Maybe it was something like this. This was the I'm sorry, that very bad drawing. This was the true distribution maybe. That's why the average of the 100 boxes is occurring here. Okay, maybe the true distribution is this red distribution, not the blue. Okay, this is our H1. This is our H1. And this is H0. Now, I'm not sure. I cannot make the claim that, based on this only 100 boxes, I cannot claim that the true mean of the general population is red. I cannot say that, okay? I cannot say that. I cannot, but at least I can make the following claim. Based on the evidence I have, with some confidence, I reject the null hypothesis that the mean of the chocolate boxes is 1 pound. I reject that based on the evidence I have. Okay, that's all I can say. I hope this part was clear. If this is clear, I'm gonna move to the next part. Okay. And then this question, why are we picking 100 boxes 1,000 times? I didn't understand. Okay. Again, this was just a, hold on, let me get rid of these. I'm not frequently using this, so okay. Just trying to raise this. Okay. Yeah, let me get rid of this one. Sorry about that. Okay. So the question is, why are we doing this part? This is hypothetically, okay? Hypothetically, what I'm doing is, if the general population, oh, these guys remained here. No, I'm gonna delete them. If the mean of the all chocolate boxes that are produced in that factory, if I had a chance to measure the weight of each and every chocolate box, the average would be 1. Okay, but again, this is not so practical. What we are gonna do is, we are going to repeatedly sample from this production line, and then measure their average weight and record. Average of the first 100 boxes, average of the second 100 boxes, average of the third 100 boxes. Because I'm not going to be able to measure average of the entire population of chocolate boxes. Okay, so but I can maybe repeat this experiment, average of the 100 boxes. I can repeat this many times. If you repeat this many times, then the average weight of these 100 boxes, when you put them into a histogram, put them into bins and create a histogram, it's going to look like this curve. Its center is going to be the average of the population. All right. Let me get rid of this one too. Okay. Actually, we covered a lot of important stuff here, right? So we are almost ready. Okay, let's look at these numbers. So what are these numbers now? Now we have I hope that we know what this shaded area is. Okay, given our assumption about the null hypothesis, this blue colored area is indicating rare events. Okay, indicating the region where rare events are occurring. Now, if my 100 boxes appear in this region, the average of 100 boxes appear in this region, then I'm going to have some questions. I will question my null hypothesis. And I will question my null hypothesis with some confidence. How confident? So I'm going to use certain thresholds. If you don't use a threshold here, okay, I mean, the average of the 100 boxes can fall in any place here, right? So here we colored this into blue, right? Based on this threshold. So what is the threshold? I can make it a little bit to the left, a little bit. Imagine that this threshold, this line, this black line, okay, was closer to mu. So what would you expect if these lines were getting closer to the center? So we had more blue area. So what would this tell you? If we had more blue area, then we would increase, look, I'm saying something, we would increase the possibility of incorrectly rejecting the null hypothesis. Why? Because when you sample 100 boxes from the production line, right? So you are actually increasing the region where you are going to consider rare. So if you have more and more area under the curve colored, then it's going to become less rare and rare, right? Because as you go towards right, what you are doing is you are getting far away from mu. As you go towards left, you are getting far away from mu. That means the average of the 100 boxes being much less or much bigger than mu is becoming more and more rare. It's becoming more and more difficult, right? If the average of the boxes is mu. But if you move threshold towards the center, then you're gonna increase the chances of having more boxes with mean appearing in this blue region, right? Mu is the average, this one, mean. So we are using mu as the Greek letter for mean, okay? Mu. All right. Now, let's look at this, what is it? Let's try to understand what is happening here. So remember, if the average of the 100 boxes appear here, I'm going to reject my null hypothesis with some confidence. What is that confidence? Right? So here I am adjusting my threshold. So imagine that your threshold is this. We call this significance level, 0.01. This 0.01 is corresponding to a point on this x-axis, which is going to indicate the area under the curve being 0.01. This area under the curve, if this threshold here is 3.30, if this threshold here is 3.30, area under the curve is going to be 0.01 divided by 2 and 0.01 divided by 2. Okay. If alpha is 0.1, then the threshold corresponds, this alpha values are indicating area under the curve up to a certain threshold value, like this threshold. If this threshold value is 3.3 and negative 3.3, the total area under the curve is 0.01. If the threshold is set to 2.58, negative 2.58, because this curve is symmetric, then area under the curve on both sides, the total area on both sides will be 0.1, and then the total area under the curve will be 0.05 if you set your threshold to 1.96. As you see, as I move from right to left, as my threshold is getting from closer to the center from right to left, alpha value is getting bigger because area under the curve is getting bigger. Okay? So these alpha values are going to be giving me some idea about how confident I will be when I say I reject the null hypothesis. Okay. So then practically, how are we going to solve problem? Let's say the average grade of students from a test, okay? I only tested 20 students, okay? But I am claiming that the average grade of students from a test is 80. I only have 20 students, but the student body is, let's say, 10,000. There are 10,000 students in the school district. And then I'm making the assumption that the average of the students in a certain math test is 80, but I only have 20 students I tested, okay? Okay, remember, my null hypothesis is 80. So I place my null hypothesis 80. And given this hypothesis, what is that, average value, then I'm going to set my threshold to some value. Let's say if my threshold is set to 1.96, I'm going to talk about Z. What does that mean? Please be patient. We're going to talk about them in more detail. If I set my threshold to 1.96 and negative 1.96, this is the area under the curve, which is going to be equal to 0.05, this area, okay? That is my critical region or significance level, 0.05. All right. Now, if 20 students, the average of 20 students from this test is, let's say, 90, which is going to be falling into this blue region. It's going to be Z equals 2 point something. And we're going to see how 90 is corresponding to 2 point something. We're going to see, we're going to write the code for that. If 90 is falling into this region, then what I'm going to say is I'm going to reject my null hypothesis that average of the students in this test is 80 with a confidence level of, or significance level of 0.05. In other words, if I set my significance level to 0.05, given this 20 students average grade, which is 90, I'm going to reject the null hypothesis that average of the entire student body is 80. Okay. One more thing, then we'll start typing the code. A lot of times, I see when I talk with students about hypothesis testing, a lot of times I see this confusion about type 1 error and type 2 error. So what does that mean? Let me very quickly explain this, and then we'll start writing some code. Again, actually, it's sometimes we also use false positive, false negative. I don't like using false positive, false negative. So I like false positive, false negative when we are using when we are testing what is that, a classification algorithm. But here, because what is positive, what is negative, it's not so clear. I like calling them type 1 error, type 2 error. Again, let's remember what is H0 and then H1. H0 is my null hypothesis. Okay. H1 is my alternative. Okay. Again, in reality, I will not know with 100% certainty which one is correct, which one is incorrect. I will not know that in reality. I will only going to I'm only going to reject one based on data with some confidence level. Let's say the null hypothesis was true if it was true. Okay. Let's say you are trying a new color. So the current color is yellow. Okay, let's write it. H0. Color is yellow. What is color? The color of the button. Okay, color of the button is yellow. Changing to red does not have any effect. Okay, so that is my null hypothesis. And in reality, again, if there was a way for us to know that this is actually true, if that is the case, and what is our alternative hypothesis? Changing the color into red has an effect. Okay, has an effect. So this is the alternate hypothesis, and somehow, based on the data, based on my calculation, somehow I said I reject the null hypothesis based on the data. Okay, I made some analysis based on the data, and then I reject the null hypothesis. But remember, null hypothesis was actually true. Okay, I rejected a null hypothesis that was actually true based on the data. Then I am making a type 1 error. Okay, H0, the null hypothesis, was actually true. In other words, in this case, there was no effect of changing the color, but somehow I changed the color into, I said changing the color has an effect, and then I reject null hypothesis. Then I make type 1 error. Well, if I say changing the color doesn't have an effect, if I don't reject the null hypothesis based on the data, then my decision is correct. Okay, that is type 1 error. Okay, this is type 1 error. Okay, type 2 error is very similar to this one. H9. This time, changing the color. Again, color has no effect. That is my null hypothesis. Always null hypothesis, no effect. Changing the color has effect, and that is my alternative hypothesis. And this time, null hypothesis is not correct. Let's say in reality, in real world, if we had full knowledge of all aspects of the universe, right, then we would see that changing the color has no effect, right? Well, changing the color has effect actually. That means null hypothesis is not correct. Okay, and then based on the data, we fail to reject the null hypothesis. Let's call this reject H0. So what happened is H0 is not correct. Actually, we should reject it, right? But based on the data we gathered, and then based on our analysis, we are saying that, hey, we don't have enough evidence to reject the null hypothesis. What is the null hypothesis? Changing color has no effect. Is that true? It's not correct. It's not correct, but we don't know that. And based on the data and our analysis, we say we don't have enough data to, or enough evidence to reject the null hypothesis. Actually, we are making a mistake, and that mistake is type 2 error. So this is type 1 error. And this is type 2 error. Okay. I hope this part was clear. So you are 95% confident, maybe it's not 80. So here, yeah, if you look at here, that you can say. So I am rejecting the the null hypothesis that mu is 80 with 95% confidence. Okay, now if you guys are ready, let's now start typing some code together. Okay, oh, I see. Take one sample to check the null hypothesis, the final conclusion. So Garima, so am I going to take only one sample to check? You don't have to take one sample. You can take multiple samples if you like, if you want to see. But in general, what we do is we take one sample that's more realistic. So we take a sample. So you have only, let's say, 40 students that took the test, or you have 1,000 students took the test, but the student population is millions, right? So you're going to consider all the students in one sample. Okay, and based on your data is in one group data, right? So based on that data, which is one sample, you're going to make some analysis and then say whether I can reject the null hypothesis or I can fail to reject the null hypothesis. Okay, so let's do some coding. First of all, let's try to understand this. Again, the code is given here, so you don't have to worry about if you cannot type it fast because you have the code, but let's do it together. I strongly recommend you also type the code yourself and then see how it is going. For what I'm going to do is, first of all, this import, I'm going to say import this SciPy. SciPy is a library in Python that we are using for statistical analysis. All these probability distributions. You can use NumPy for that too. But my suggestion is pick one of them first, learn how you can create random variables, how you can make your calculations with one library first, and then learn the other one, because I see a lot of times students are getting confused. Oh, sometimes they are using NumPy random, sometimes they are using SciPy rand, and then they get confused. Make sure that you focus on one of them, be comfortable with it. You can use the other one if you like. So I'm going to use SciPy stats. Okay, I'm going to import SciPy stats. Okay, as, let's call it ST. Okay, SciPy stats as ST. Okay, that's the first thing. Second, I'm going to use from this library, I'm going to use normal distribution, NORM. Okay, normal distribution. So this normal distribution has, we can create with this normal distribution, if you like you can create random variables with some mean and standard deviation. Okay, so in the place of mean, you can put, let's say, 0, and then standard deviation 1. If you run this, and then it's going to give you an error because there is no SciPy. So it's just going to give you some random variable which is normally distributed with mean 0 and standard deviation 1. If you like, you can generate 100 of them. Okay, here I generated 100 of them. Okay, that's the first thing. What I want to generate is, I want to generate this normal distribution. Okay, so how can I do that? So these are simple things, but I strongly recommend using simulations to practice your statistical knowledge. Okay, you will see it makes a huge difference if you simulate what you learn. All right. Okay, so how can I generate this normally distributed, this curve for normal distributed, or we call this Gaussian distribution? So what I'm going to do is, first, I am going to generate these numbers on the x-axis. Okay, I'm going to generate the numbers on the x-axis. So let's do that. So for that, I'm going to import NumPy as NP. And then I'm going to say NP a range. I'm using this one. I'm going to create numbers from -5 to 5. Actually, -5 to 5 is a little bit big. So let's use -4 to 4 with steps of 0.01. So I'm going to start from -4, then -3.99, then -3.98. So basically, let me yes, if I do this, it's giving me all these numbers, starting from -4, then -3.99, -3. That is what this NPA range is. Okay, these numbers are indicating x-axis. So let's call this sample space. Let's call it SP. Okay, now, given these numbers, the next thing what I'm going to do is, if I have the normal distribution, N, let's call this N, and normal distribution with some mean and standard deviation, sigma. Okay. So if I ask you the question, what is the probability that x is less than 3? What does that mean? If x is normally distributed, it's a normally distributed random variable with mean and sigma. So with mean, in this case, mean is, let's say, 0. Sigma is 1. Mean is the mu. Sigma is the standard deviation. If x is a random variable, normally distributed with mean 0 and standard deviation 1, how can you find probability of x less than 3? What is this? What does that mean? So what I'm going to do is, I'm going to find x on this axis. X is right here, 3. Probability of x less than 3 is, after I find x, right? All the area under this curve up to x equals 3 is indicating probability of x less than 3. If I say, what is the probability x equals 3? In that case, I'm going to find x here, 3, and this height of this line, which is going from 3 and hitting this curve, this height is actually probability of x equals 3. Now, if mean is 0, the probability x equals 0 is going to be the maximum, this one. Because if mean is 0, most of the numbers will be around the average, right? So that's why when x is 0, the probability is going to make the peak, okay? If x is less than 0, the probability is going to get decrease and decrease. If this is a normal distribution, right? This is a normal distribution and variable. And at some point, the probability is going to get very small. In other words, from a normally distributed random variable with mean 0 and sigma 1, it's very, very unlikely that you're going to have a number which is less than -4 or greater than 4. Okay, so that's the reason why I first generate x's, and then I'm going to find this height from that x value, this height, so that I can plot this curve. So how can I find, and by the way, this height, which is probability of x equals 3, probability of x equals 1, probability of x equals 2, okay? So how can I find these values? For these values, I will be using probability density function. I'm writing it, probability density function. Okay, so let's do that. Let's do it now. I'm going to spend time for this example. The next example, I'm not going to spend that much time. So given this SP, what I'm going to do is from this SciPy stats, which is ST has a distribution called normal distribution. This normal distribution has a function called probability density function. Okay, probability density function. I'm going to find the probability density function of my x values. This time x is not just 0, not just 1, not just 2. It is all the values from -4 to 4. Okay, that is my sample space. Okay, and my normal distribution has 0 mean and standard deviation 1. Now, when I do this, it is actually giving me the probability density function, or the height of this line, this perpendicular line, okay, on this curve. So let me make this, what area? So probability density function, PDF. Okay, perfect. Sure, Karim. I'm gonna talk a little bit more about that in a minute. Okay, now I created the PDF values. Now I'm going to plot them. So let's import matplotlib dot py plot. Okay, so this is used for plotting figures as PLT. This is the abbreviation. I will be using PLT for this entire thing. I'll be using NP for NumPy. I'll be using ST. So you can pick anything. You can write anything here. This is your way of representing this long expression. So I will use PLT dot plots. Okay, plots. I'm going to use SP. This is my x-axis. PDF is the y-axis. And then I'm going to hit, let me make this one. I'm going to hit enter, and it's going to plot. As you see, I created a normal distribution x values are from -4 to 4, the height from each x value is indicating the probability density function, okay? Probability density function. So why are we doing simulations? When you take an interview, okay, when you take an interview, like a data science position, right, or statistics position, if they require, and most of the positions require you know coding, right? Not as much as a software engineer, but coding enough for you to do your project, your job. So they might ask you some questions. For example, can you find, I know that I'm a little bit, so if X is distributed Poisson with lambda equals 3, okay, can you find probability of X less than 3 given, okay, X is X is also greater than 1. Okay, I'm just making up, okay? So can you find this probability, not mathematically, but can you find this probability by a simulation? Like, can you write the code to find this answer? Okay, so that's one thing. Another thing is a lot of times to understand inner wirings of all these testing. So it's good to run simulation and then control the environment yourself and then see when you change one variable, how things are changing. Okay, I find it extremely useful to understand concepts when I write the code and then control what is happening and then see myself. Okay, so this is very, very useful. Okay, anyway, so I just wanted to show you how we can generate a normal distribution. So there is no reason for me to now explain the rest because the rest is you can write the code yourself. One thing here is we mentioned two things here: PDF, probability density function, RVS, random variables, and there is one more, CDF, cumulative distribution function. So what is cumulative distribution function? Remember I said, can you find probability of X less than or equal to 5, right? So what is this equal to? It's equal to cumulative distribution function where X equals 5, right? So what does that mean? Probability of X less than 5, it means probability of X equals -4 plus probability of X equals -3 plus, of course, in between there are so many different numbers, and then plus probability of X equals 5, right? So this is I'm adding up all the probabilities for each X value where X is less than 5. So this is the cumulative value for this probability, okay? And this is the cumulative distribution function. As X is moving towards right, the cumulative distribution function value increases, and at some point it's going to get fixed at 1. Okay. All right. Now let's move on. This is Gaussian distribution. When you are working on hypothesis testing, please make sure that you are comfortable with 3 distributions. First, normal distribution, like Gaussian distribution. Okay, we just learned. And then under normal distribution, it's not a different distribution, but under normal distribution, we're going to spend some time on it. Z-score or standard normal distribution. Z-score is standard normal distribution value, that's distribution. Okay. And then T-distribution. Okay, make sure that we are familiar with these two. Okay. Now, we just learned about normal distribution. I'm going to talk about Z-score later. And now we are talking about T-distribution. It's T-distribution or student's T-distribution. It's the same thing. Okay. So let's go back to the hypothesis testing one more time. Here. Right? We have a new hypothesis. We have an alternative hypothesis. There is a population. So now let's write. Right? There's a population out there. So this population can be chocolate boxes. Okay. The entire set of boxes. Okay, that is the population. Okay. And then we, most of the time, do not know the variance. Okay. And then, of course, we do not know the mean, right? So most of the time, we don't know the variance and we don't know the mean. Okay. And then what do we have? All we have is a sample of 100 boxes. That's all we have. Okay. So we have H0 and H0. So H0 and H1. So these are our hypotheses. There is a population of chocolate boxes out there. We don't know the variance. We don't know the mean. Variance is sigma. Mean is mu. All we know is 100 boxes. Okay, that's all. Now, using this 100 boxes without knowing these two, can we have some confidence? Can we reject or fail to reject null hypothesis with some confidence level? So to be able to do that, okay, to be able to work with this problem with only using 100 boxes, we are going to use this T distribution. Okay, this is just a very general overview of why suddenly we began to use T distribution. T distribution is very, very close to normal distribution, the way it looks. Actually, the more samples you have, the more T distribution will look like normal distribution. And after a while, when you have more samples, T distribution will be exactly the same with normal distribution. So please keep this in mind, okay? Second, again, I'm going to be using SciPy stats. This time, the distribution is T. Earlier, the distribution was normal, okay? The distribution was normal. Now, rather than normal distribution, I'm using T distribution. Okay, that's all. That's all. The rest is the same. Look, again, I'm creating sample space. This time, this is all I have. This is number of chocolate boxes, okay, that I have. Degrees of freedom is this 100 chocolate boxes minus 1. That is degrees of freedom. And this is how I generate probability density function from a T distribution. All I need is my boxes and degrees of freedom. And this will give me the figure that I had earlier. So I'm not repeating this because we already did for normal distribution. The only difference here is I have one more parameter for T distribution. What is that? Degrees of freedom. What is it? Number of samples minus 1. Okay, let's note that much. Another distribution, which I'm not going to spend too much time on this now, chi-square distribution, which we are using to run tests for categorical variance. Let's put this aside for now. Okay, let's put this aside for now. But I put it here. Okay. Now, this part is important. Let's practice this together. This is going to be the confusing part. Okay, so now we are into why we are doing simulation, why we are using coding, because we want to understand. Okay, we want to understand things better. Okay, again, from SciPy.stats. Let me not from imports as ST. Okay, so I'm going to be using normal distribution. So this time what I want to do is, if I gave you the area under the curve, can you find the threshold? So what does that mean? What does that mean? I'm going up to the very early figure we used here. Okay, if I give you the area under the curve, let me make this smaller. If I give you the area under the curve, can you find this threshold? Here, z equals 1.96. When you are right here, the total area under the curve up to this point, which is z equals 1.96, the total area under the curve is 0.95. Okay, if I tell you area under the curve is 0.95, what is the corresponding threshold? Can you find it? Later, I'm going to give you, if this is threshold value, can you find the area under the curve? Okay, can you move from area under the curve to z value, from z value, which is threshold, z value to area under the curve? Can you move back and forth between area, z area? Can you do that? Okay, so that's what we're going to do now. Later, we're going to put all these pieces together, and then we'll solve really complicated problems. Okay, let's see, hopefully. So let's see. All right. Okay, this is the question. If I gave you the area under the curve, can you find the threshold? in parentheses z-score. I'm going to talk about z-score after this, okay? In a minute. Okay, this is the question. Now, I imported my stats library, and then this is the area under the curve. I'm going to denote it with p-value, okay? P-value, and then we're going to talk about p-value again. I say talk about, we will. This is 0.95. It is the area under the curve. Now, what I want to do is, what threshold value corresponds to 94? Remember, it was 1.96. Let's see if we can get 1.96. So I'm going to use my stat library. From my stat library, I'm going to use my normal distribution. Remember, so far I know how to find probability density function, which is the height of the curve corresponding to some point on x-axis. That is PDF. I also learned about how I can create random variables, right? I also learned about cumulative distribution function, which is what is the probability that x less than 5? That is the answer, cumulative distribution function. But this time, I'm going in the reverse direction, okay? If I give you the area, can you find the threshold? So for this, I'm going to use percent point function, PPF, percent point function, okay? So this is the area, P value, this is the area. Can you find me the corresponding threshold for this area? Let me run this. 1.64. So let's see. I'll go up. By the way. Yeah. So, by the way, the example we saw earlier up here, the area under the curve was 0.975. So I made a mistake when I said 0.95. Which one? This one. So if the middle area is 95%, the sum of these two blue region is 0.05. That means one blue region is 0.025. That means the area under the curve up to this z value is 0.975. Okay, let's go back. Let's verify that. Okay, what if p-value is not 95 but 975? Okay, then what is the threshold? Okay, 1.956, which is 1.96. So we found area, we found the threshold if the area under the curve is 0.975. Okay, now let's make this value equals and print this value. Now let's go back from the threshold to the area. Given this area, now again, ST, this is my package, library, I'm sorry. And then this is my distribution norm. And then this time I'm going to find cumulative distribution function value for this 1.96 value. This time I give the threshold, try to find the area. Okay, now let me assign this to p-value and print p-value. Let's see. Okay, perfect. So given the area under the curve, I'm able to find the threshold. Given the threshold, I'm able to find the area under the curve. So I can move back and forth between area under the curve and z-score, and area under the curve. Okay, now I keep saying z-score, z. Let's talk about it. Okay, that's an important issue. Let's talk about it now. For that, you need to have some what is it? Stat knowledge. That's fine. If we don't remember, let's remember it together. I'm going to copy the code we used earlier, so I don't want to take your time. I'm just going to copy this code in here. Let's see. This one, this code in here. Okay, let me just copy this one, okay? Copy this one. So we can use this for our Z discussion here. Okay, let me clean this a little bit. I don't need this part, and I don't need this part. Okay, what I'm gonna do is, again, these are the x-axis values. This is my normal distribution. Remember, this is ST norm, probability density function. 0 is mean, 1 is standard deviation. So I'm gonna change these numbers, okay? Let's see what's gonna happen. So I'm gonna make this 10, mean is 10. And standard deviation, I'm going to make is 3. And then I'm going to plot this figure. Now, as you see, I'm only able to see a part of the figure. So let's make this figure going from negative 7 to positive 7. Actually, much bigger than positive 7. It should be positive 14. -7, and then let's make this small. Yeah. Okay. So at this, we can see that this is our new curve. The center is 10 because I've made the center equals 10. The standard deviation is 3. Okay, standard deviation measures how the data is spreading around the mean. Okay, let's keep this in mind. So this is a normal distribution with mean 10 and standard deviation 3. So if I give you a random variable, and ask you what is the expected value of this random variable, this is actually nothing but the average, right? Mu. Now, if I take this random variable and subtract a number from this random variable and ask you what is the expected value of this subtraction, then the expected value will be mu minus a, right? We know this. We know this from our stat class. So this is what exactly I'm going to do now. All right, this is what exactly I'm going to do now. So what I'm going to do is, remember these SPs, these are the numbers. These are the x's. These are the x's. So you see x number, x is like 4, 6, 8. So x is representing the numbers on the x-axis. So I'm going to subtract from SP, I'm going to subtract 10. Okay, SP equals SP minus 10. Actually, this is exactly what I'm doing. So A is 10, X is SP. X is capital X is representing these numbers on the x-axis. And then I'm drawing this figure one more time. Okay, and then I'm drawing this figure one more time and then see what's going to happen now. Oh, by the way, yeah, if I do this, I need to change the normal distribution to, yeah, it's not going to work this way. So let's go back here. The expected value of x minus a will be mu minus a, right? So then I'm going to subtract from this mu, I'm going to subtract from this mu 10. Okay. Now let's run this. Okay. So as you see, the same figure, which is shifted, this time the center is 0. You see, originally center was 10, but because I subtracted 10 from all my x values, the expected value also is shifted to 0, okay, which is 10 minus 10. Please, let's understand this because this part is important. And then can we use two-tail or one-tail thing in the code? Yeah, we are going to use two-tail and one-tail in the code. Okay, that's the first thing. If I subtract a from all my random numbers from a certain random distribution, then the mean is going to be shifted that much. Okay, that's for sure. Next, if I take a random variable, and then measure its variance, let's say its variance is sigma. Okay, if I multiply that random variable with some a, then its variance is going to be sigma times a squared, right? Sigma times, so this is sigma times a squared, right? We know this from our statistics course. Okay, now I'm going to use this. Let's say I give you a normal distribution with some mu and some sigma. Okay, x is distributed normally with some mu and some sigma. Sigma is the standard deviation, mu is the mean. And by the way, standard deviation is square root of the variance. We know that, right? We know that. All right. If I give you a random variable x, which is normally distributed with mu and sigma, and then if I subtract from this x, as I did in here, I'm subtracting from x A. And then let's be more specific. A is actually mu. Be more specific. Remember, mu is some number. Mu is the average of x. I'm subtracting average from all x's, as I did in here. Okay. All right. Then if I take the mean of this, if I take the mean of this, we know that this is going to be 0. We just showed that. We just showed that. Okay. Next. I take x minus mu. I take x minus mu. And then I divide this number. In other words, I multiply this number. You see, I'm multiplying x minus mu by a number, a. Now, rather than multiplying by a, I'm going to multiply this by one over sigma. Okay. So what I'm doing is I'm multiplying x minus mu by 1 over sigma. Okay. Let's say this is my x nu. So in that case, what is the variance? What is the variance of x nu? Let's calculate that. What is the variance of x nu? It is variance of x, okay, divided by sigma squared, and then minus variance of mu divided by sigma. Okay. This part is 0. This is 0. Variance of a constant is 0. So variance of x nu is variance of x divided by sigma squared. In other words, standard deviation of x nu will be what? Standard deviation of x divided by sigma. What is sigma? Standard deviation of x. Then standard deviation of x nu will be nothing but 1. Okay, so this part is important for us to understand what z-score is. What I did is I started with some normal distribution. I showed that if I subtract mu, which is the mean of that normal distribution, from the random variable itself, the mean is going to be equal to 0. Next, what I showed is if I take this x minus mu and multiply it by 1 over sigma, and I call it x nu, this is a new distribution now. The standard deviation of this x nu is 1. The mean of this x nu is 0. We just showed that. Basically, this is important. Basically, x nu is nothing but standard normal distribution or z distribution. Okay. In other words, given any normal distribution, you can convert it to z distribution. This is going to be very important in our A/B test. Okay, this is going to be very important when we get to our A/B test. Yeah, this is a lot of math. I know that it's getting boring now. I know that. I'm aware of that. But please try to internalize this part. Okay, this part is very important when it comes to making all these calculations for evaluating your A/B test. Okay, we will always turn things into z-scores. Okay. All right. Now we have some idea about z-scores. We're going to get back to this one when we are dealing with A/B test. We are going to use all these calculations. We know how to move back and forth between thresholds and between the area under the curve and threshold and area under the curve. We can do the same thing back and forth for t-score. Okay, let's say this is the area under the curve. If this is the degrees of freedom, remember there is one additional parameter for t-score, which is degrees of freedom. So we can find the threshold, or given that threshold and degrees of freedom, we can find the cumulative distribution function, which is area under the curve. This is for t distribution, and this is for, what is that? Normal distribution. Okay. Again, you have the code. You can practice yourself. Now it is time for us, and I'm going to finish with this one. It is time for us to actually test one hypothesis, given all these boring explanations. All right. Okay, let's look at this example here. A popular electronic. So before getting into example, you see this one. You see this one. I just try to explain this part. Okay, this mu0 is the mean. This one. Mu. Okay, mean. I'm subtracting mean and then dividing this subtraction by sigma. So this is what is this. Okay, that's why I spent time on there. Subtracting mean and dividing by sigma. What is the sigma of the standard deviation of a sample? If you know the standard deviation of the population, then population divided by square root of the sample size. Let's do it together, and then hopefully we are going to be comfortable with it. Okay, so what is the question here? So we want a popular website, electronics website, that tries to determine whether a smartphone has a 7.8-hour battery life, as claimed by the manufacturer, because some of the users were complaining about poor battery life. Okay, so this is the claimed number. In other words, this will be your H0. What is your H0? The battery life is 7.8 as claimed. Okay, what is your data? The data is the battery life that you collected from some users. Now you are going to use this data to see if you can reject or if you can fail to reject the null hypothesis. Okay. The website sampled only 10 smartphones. That is your data. And then the mean of these 10 smartphones is 7.6. So this is the mean of 10 smartphones. This is the claimed mean of the population. Okay, claimed mean of the population. All right. And the population standard deviation of battery life is 0.57. This is very unrealistic. It's going to be very unrealistic for us to know the standard deviation of the population. In general, we don't know that. But in this question, we know. Later, we are going to consider what if we don't know. So we don't know the standard deviation. So in this case, we know the standard deviation of battery life is 0. Probably these guys did a lot of tests in their factory, and they determined that this is the mean and this is the standard deviation. Okay, all right. Does sufficient evidence exist that the battery life of the smartphone is actually lower than the manufacturer's claim at a significance level of 0.05? So this is our significance level. In other words, if what the manufacturer was saying was correct, this is how we would observe the curve centered at mu equals 7.8, or if you turn this into a z distribution, z equals 0. Z equals 0 will correspond to mu equals 7.8. And this is the region, okay, where the average of the 10 average battery life of the 10 smartphones is occurring. Now, our goal is whether the region where this average is occurring is in a region where we can consider is a very rare occasion. If it is a very rare occasion, then we have enough evidence that we are going to reject the null hypothesis. Okay, that's what we're going to do. So what we do is here, we find the z-score, which is the threshold for 10 smartphones. What is the average of 10 smartphones? 7.6. What is the mean of the population? 7.8. So we are trying to see where the 7.6 is located on this x-axis, which is in this case z-axis. We subtract 7.8, which is the mean, from 7.6, which is the mean of the 10 smartphones. 7.8 is mean of the population. And divide by the standard deviation of the sample, which is population standard deviation divided by square root of the sample size. Okay, this negative 1.11 is the threshold or the point where 7.6 is located on distribution, okay, on the z-axis in this distribution, and this distribution is representing our null hypothesis, where the center is 7.8. In this case, it is corresponding to 0. All right. So now our job is z equals negative 1.1 too far away from 0 or close enough to 0? If it is too far away, then we're going to reject the null hypothesis. What is that? It means 7.6 is such a rare event if 7.8 was the true average battery life. So I just put the code in here. So let's write the, go over the code together. Again, I solved this problem in multiple ways. Let's, I believe I solved the problem. Yeah, I solved it multiple ways. Actually, I created simulations to make things a lot more. So as you see, all these are for this problem. Okay, I tried to open it up. How to decide on a sample size when designing? Oh, that's essay. This is a more advanced question. It will come later. So when you decide the sample size, you need to consider your alpha value here, this alpha value, which is this one, this confidence significance level. Where is it? Where is it? It's here, this alpha value. Not only that, for experiments, alpha is one input to make a decision on sample size. The other one is what you find, is it going to make any, in terms of business, is it going to make any sense or not? So for that also, we have another variable, another parameter. So we're going to use these two parameters to decide on the sample size, okay? So next week, hopefully when we are simulating and then analyzing an A/B test, we are going to also look at how we can set the sample size. For sample size, we are going to use alpha as well as one additional variable, which is representing business significance of the finding in terms of business. So when I say this, let me just give this additional explanation. Let's say you are trying to decide whether placing a button, changing the button color from yellow to red, whether it makes sense or not, okay? So what does that mean? There are two things we have to consider. One is whether the number of people who are going to click on the red button when you change the color, is it increasing significantly at some alpha value? Okay, that's the first thing. And then second is that increase makes sense in terms of business? So sometimes the change statistically is significant, you can see that, but then the change is not enough for you to decide for implementing it, to moving forward with that project, okay? So we need to consider these two to decide on the sample size. Oh, is this recording going to be available? Yes, yes. For reason, those JPEG file, yes. Link, that's my mistake. Normally, I should embed the JPEG files in Colab first. So normally, I embedded these JPEG files into Jupyter Notebook. When you open it in Colab, you don't see the JPEG files. When you open it in your Jupyter Notebook, you will see them. Normally, I should fix it. I was lazy. I didn't fix it. Yeah, that's not your that's not something on your side. It's my side. Can you give me a real-time example of why T distribution is used over normal distribution? Real-time example of T distribution. We are going to use T distribution when we don't have enough number of observations. When we have, let's say, that some people say 30 observations, some say 50, but let's say 50 observations. When you have more than 50, T and normal distributions are actually almost the same, right? So then what is the reason we are using T distribution? The reason is when we are using T distribution, we don't know the population sigma, the standard deviation of the sigma and standard deviation, and also mean of the population. So we are lacking these two pieces of information. So that's why we are not using regular Z distribution. So T distribution is actually created by sampling from normal distributions, right? When you don't know the mean and the standard deviation. So that's why we are using T distribution over Z. So I have one example actually. Hopefully I can share that with you, where you can simulate T distribution. Okay, you can simulate it. It's not without using any functions coming with Python. So it's going to give you an idea about why we are using T distribution. Actually, I was planning to go over that example with you today. I couldn't find the example. Maybe let's see, was it here or in the other file? If I can locate it, maybe we can go over it together. I really don't remember if it was here or in the other file. But yeah, I understood why you are asking this question. And this is one of the things when you first learn about T distribution, getting confused. Why suddenly we are introduced with T distribution? Why not we use normal distribution? Because when you don't know the mean and the sigma of the population, normal distribution is not going to be giving you accurate results when you have small number of observations. And I know that this is a very vague explanation, but when you have small number of observations, we go with t-distribution. Is this, it should be used t-distribution in this case? In this case, we should use t-distribution, but I'm using normal distribution for this. Yeah, you should use t-distribution for that. But hold on. But yeah, t-distribution for this, the thing is we know the mean and the standard deviation. We know the mean and standard deviation of the population. That's why I'm using this distribution here. Is this recording going to be available? Yeah. And can you give me, yeah, is CDF same as area under the curve? Area under the curve is different, Abhimanyu. So area under the curve is, we are using this as a metric for classification models. Cumulative distribution function is for random variables to find out what is the probability, say x less than or equal to some threshold. So you set the threshold and you are finding the area under the distribution, right? So that area under the curve is different than AUC that we are using for classification problems. In this case, if H0 is true, what is the p-value range? If in this case, if H0 was true, actually, we don't know if H0 is true or not, we don't know, right? But let's say H0 is true. If, let's say, this is the case, and then let's say the average, which is 7.6, is appearing at a position where close to the mean, then we are going to say we are not rejecting the null hypothesis. So in this case, if H0 is true, what is p-value range below 0.05? So I didn't get this part of the question, Jay. So if this is true, and if sigma is 0.05, in this case, we are going to reject the null hypothesis. And then if null hypothesis was true, then we were making a type 1 error. Let's write the code together for this one. Okay, hold on, we did this one. Oh, I did this for another. Okay, no problem. So yeah, let's write the code for this one. Again, let's import SciPy. I know we already imported, but for you to practice, I'm writing it over and over again as ST, okay? So, all right. And then this is for this distribution, actually. I just wanted to show you how the distribution looks like. Let's go to the solution. Yeah, solution is here. Okay, let's do this. Okay, import. Sorry, stats. Okay, now what I'm gonna do is, these numbers are given. These numbers are given. X bar, what is X bar? X bar, that is the average of 10 cell phones, right? So it is 7.6. This is sample mean, okay? All right. What is 7.8? What is that? This is claimed population mean. Should be true if H0 was true. And we don't know if H0 is true or not. We don't know that. Okay. What else? Sigma is 0.57. What is this? This is the claimed STD of the population. Okay. So we are going to treat these guys as true for now. Okay. All right. Okay. Let's continue. Now, N is 10. What is this? Number of cell phones, right? Their batteries are actually measured. Okay. Now, what I'm gonna do is, look, I'm writing here, I will generate the z-score for X bar. So I need to scale X bar to z-score. What is z-score? Z-score is changing from -3 to 3. I need to scale my X bar to 0. How am I gonna do this? Remember how we calculate z-score? I tried to explain earlier. I'm gonna subtract the mean. So let's do that first. X bar minus mu. I first subtract the mean so that I brought X bar into the distribution where center is 0. Okay, that's the first thing. And then I'm gonna divide this by sigma of the population. I'm sorry, not population. Sigma of the standard deviation or standard deviation of the sample. What is standard deviation of the sample? Let me write it here. Over, okay, n to the power of, I will stop soon, okay? I know we are tired. Okay, this is, let's call this STD sample. Okay, let's call it this way. Okay, this is the STD of 10 samples. So I'm dividing this guy with STD of sample. Okay. Now this is the Z score for the sample. Okay. I found Z score for the sample. All right. Next. Now I know the Z. Remember, I can go from Z to area cumulative distribution function, or from cumulative distribution function to threshold, Z. Z is the threshold. Now I know how to find the area under the curve up to that Z value. I know that, right? So let's use that. ST is my library, dot norm is my normal distribution, dot cumulative distribution function, okay, of Z sample. If you don't say anything about mean and standard deviation, by default, it is Z distribution, okay, by default. Okay, I found this. Let's call this P. So this P is the area under the curve. So let's print the P. Let's see what print P. So what is this? 0.13. So what is 0.13? Normally, area under the curve, the whole area is 1. The whole area is 1. 0.13 is somewhere here. So what was our alpha? What was our alpha? Alpha, oh, I didn't put alpha in here. Alpha is what? Here. Oh, alpha is 0.05. Let's write it here. What is alpha? The area under the curve indicating the rare occasions. Okay. So if our P is less than this area, that means our Z, the threshold, is falling into that rare occasion. In other words, our mean of the 10 cell phones would be falling into a region which is indicating a rare occasion. Okay. If P is less than alpha, then the average of the 10 cell phones will be falling into a region which is indicating the rare occasions. So that's why I'm writing this if statement here. If alpha is this, if the notebook with explanations of the recording will be sent, yeah, recording will be available, and then we can give the link to this notebook. Okay. If P is, I'm going to write this. If P is less than alpha, that means if P is less than alpha, that means those 10 cell phones are falling into that region which is represented by those very rare occasions. Again, remember, there are two explanations. Either everything is happening by chance, or the actual mean of the battery life for all the cell phones is less than 7.8. It's not 7.8. It's another distribution, not 7.8, right? Okay. If P is less than alpha, then I'm going to reject the null hypothesis. That means I have enough evidence to reject the null hypothesis. All right. Otherwise, let's write else. Okay. I am going to fail to reject the null hypothesis. I'm not saying null hypothesis is correct. Fail to reject the null hypothesis. Okay. And then we fail to reject the null hypothesis. So let me see. Why are we assuming mean and STD of population is 1, 0? Shouldn't it be 7.8? Yeah. Okay, so it is 7.8 and 0.57, but when we get to Z scores, okay, let me show you. That's what I tried to show you earlier, right? When it is Z score, so let's calculate the population. I'm putting it here. Calculate the Z score for the population. Calculate the well, not the score, but mean and sigma for the population as this Z distribution, okay? Distribution in terms of. Okay, let's do that. First of all, to calculate the mean of the population in Z distribution. So this is a normal distribution. This is a normal distribution. Okay. Now, in the real world, all different distributions that we see, all this data that we generate, normally, for most of them, we are making assumptions that all these data distributions we see in the real world are normal distributions. There are so many normal distributions, right? What is the average, what the distribution of people, number of things people buy on a Saturday? Okay, the distribution of books people read in summer, right? So the distribution of the grades computer science students are taking from algorithms class, right? So these are all different distributions. They are in more or less, we are making the assumption that they are normally distributed. And all these guys have a different mu and different sigma. So how am I going to compare all these different normal distributions? There are so many of them, millions of them. We are going to bring them all down to a common standard distribution so that I can compare them. So for this, I turn everything into Z distribution. So how do I do that? I take, I'm just using this formula here. So what is the mean of this guy when I make this turning it into Z distribution? This means take all the random values coming from this distribution. From all these random values, let's say X is distributed this way. All these random values coming from the distribution, I'm going to subtract from these guys mu. The moment I do that, then the mean will be 0, right? That's why I'm assuming it is 0 here. That's why this normal distribution of the population now has a 0, because that's what I do here. I'm assuming I did already, okay? All right, and then what I do is, after subtract mu from the population, I divide this by sigma. Okay, and the moment I do this, then sigma becomes 1. For this distribution, when I do this, sigma of the sigma Z, let me call this mean Z, becomes 1. Okay, so that's why I'm assuming that I already did this for the population, okay? And I'm also doing this for my sample, which is only 10 points. Yeah, this case H0, okay, J lead. So we are not saying H0 is true. We are not saying it. We are only saying that we fail to reject the null hypothesis. That's what we are saying. We fail to reject H0. H0 might be the true mean can be something different. The true mean can be maybe 8, can be maybe 8.1, we don't know. But all we know is if somebody claims mu is 7.8, with this data, we don't have enough evidence to reject this claim. We are not saying this claim is right, okay? But we don't have enough evidence to reject it. Okay. So another way I wanted to show this one, and then after this, I'm gonna stop. Okay, it's already late. I'm gonna stop for one. Maybe you can look at this this code yourself. Next time I will directly start from A/B tests. Okay, so I'm gonna leave the rest to you so you can check them yourself. So what I'm trying to do here is, again, everything is the same. As you see, the numbers are all the same. For this one, alpha is 0.05. I find the threshold for alpha, okay? And then I am showing that threshold. Where is that threshold? The critical, no, I don't show that. Okay, I use this alpha value, and what am I doing? Yeah, and then I am changing this into Z value. Okay, so this Z value, this one is the threshold of alpha on true population. You see, now numbers are 7, 8, 9. They're not, the distribution center is not 0. This yellow line is the center of the population, which is 7.8. This black line is indicating the threshold for alpha equals 0.05. This red line is indicating the average of the 10, 10 phones. As you see, the average of the 10 phones is falling to the right of the Z threshold value, or alpha equals 0.05 threshold value. In other words, average of the 10 phones is not far enough away from the 7.8 claimed average of the population. So that's why we failed to reject the null hypothesis. Yeah, you can check this code yourself. I just created this as an example. Here I'm generating random numbers. This is the claimed mu. This is the claimed sigma, and then I'm generating 100,000 samples from this population. Imagine that there are 100,000 phones coming from this distribution, okay? And then each has their own battery life. And this is the distribution of these 100,000 phones, their battery lives. And that is their mean, which is 7.8. This is 0.05 threshold point. And this is the average of the 10 phones that we have as sample. That's why we fail to reject the null hypothesis, because average of the 10 phones is not falling to the left of the alpha threshold value. And this one, another same thing. I tried to do the same thing. This time I tried to show you the critical regions. Again, this is the this threshold here, this one, this line here. This time I show it here, okay? And this is the region. If our average of the 10 was falling into this region, then we would reject the null hypothesis. But because it didn't fall into this region, which is alpha equals 0.05, the area under the curve here is alpha equals 0.05. That's why we failed to reject the null hypothesis, because the average of the 10, which is this red one, is falling to the right of this shaded area. All right. Okay, let me stop here. I think we talked enough. Let me stop here. I had another example. This time we are using a data set. Maybe next time I can quickly go over this example with you and then use some students' tree distribution. My goal was covering A/B test and then this one in 2 sessions, but I think it is far beyond 2 sessions. So again, this is a very important topic. It's I said you might be very tired. I'm tired right now. It's not so easy if this is if you have not reviewed this topic recently. It's not so straightforward. So you need to actually do some examples and coding, right? But I think this much would be sufficient for us to understand what is H0, what is H1, when you reject, when you fail to reject. If we get this part, and what is Z-score, what is T-distribution, if we get this part, how we can get from Z to area, the cumulative distribution function, and then PDF, from CDF to Z, if we understood back and forth going in between these two values, it's going to be extremely helpful when we get started with A/B test. So this is the file for A/B test. Again, I already shared this with you. This is our next meeting. So this time we're going to go over A/B test. And there are a lot of, but main, I'm gonna work on the code. Okay, I'm gonna leave the writings explanations to you. But as you see, the topics are the same. So we are still going to continue with hypothesis testing, but this time the hypothesis testing will happen on proportions, on ratios, rather than continuous variables. That's the difference. Okay, so let me stop here. Thank you so much for listening. Okay, and the video will be shared with you. And please let us know, post your reviews. So let us know how we are doing so that we can improve these sessions. So I don't know, if we go to Google and then try to write some reviews, and then I can read the reviews, and then I appreciate your feedbacks. Thank you so much. And then see you guys next Saturday. Okay, take care. Bye.